Now we are going to talk about the parameter section in the heat exchanger, but in details. At the beginning, we have a heat exchanger model. We have different heat exchanger. Before I mentioned that we usually use the simple endpoint and the simple weighted. Here we have a regular shielded tube. This one required Aspen exchanger design and rating, which is known as EDR. For this one, simple endpoint that we are going to use and this simple weighted, we are going to describe them one by one. Here, for the simple steady state rating and the dynamic rating, this one we are going to use moving forward if we are moving our simulation from a steady state to the dynamic state. Okay, so here we have chosen a simple weighted. To describe this, we have a simple endpoint model. This endpoint model, which is this one. Okay, let me select it at the beginning. If we are talking about this one, it uses the normal equation that is known for the calculation of the duty, which is Q, which is the heat, equal to UA delta T. The U is the overall heat. UA here, this is the overall heat coefficient multiplied by the A, which is the area, and the delta T, which is the difference in temperature. So this is the simple endpoint, and it is using a simple equation. Also, we have another model, which is the simple weighted. This one, simple weighted model. The simple weighted model, this one is usually used for nonlinear heat curves, and this one divided your heat curve into a small interval, and from this small interval we can calculate the duty. Okay, here we can add the information about the UA, which is the overall heat coefficient. If we choose the simple weight, we need to define the pressure drop in the shell side and also the tube side. If you don't have information about the delta B, assume at the beginning small number like 5 kPa, and after that you can increase it and adjust the values until you reach something similar to the one that you have in your plan. After that we have this section, which is we can use FT. This one you can check it or not. If you select it, this one, we are going to use logarithmic mean temperature difference. This is a correction factor. You can use it or not. It will affect the accuracy. Okay. For the simple weighted, if we use it as the simple weighted, it will be assumed to be equal to 1. Okay. Here we have the geometry, information about the geometry, like the tube passes, the number of tube passes, the shell passes, the shell in series and first pass, and so on. So this is a counter flow. After that, we have the number of intervals. Before, I mentioned that the simple weighted will divide your curve into some intervals. So this is the number of intervals. The more the number of intervals, the more accurate your numbers will be. Okay. Also, we can have here like the step type. Here we have selected the dew point and the bubble point. This one is selected. If we have selected this point, we mean that as the heat curve, we are going to have a dew point and the bubble point taking into consideration. Okay, so if we are moving from a liquid to a vapor or from a vapor into a liquid in the heat exchanger, we need to take this information into consideration. The step type, because we are dividing our curve into intervals, it could be divided in terms of enthalpy, temperature, or auto interval. In this case, we are going to keep it equal enthalpy, which means all intervals have an equal enthalpy. If we choose to have equal temperature, which means each interval that we are dividing our heat exchanger to will have the same temperature. Okay. If we choose auto interval, Aspen HYSYS will be responsible for dividing this one. Here we have a constant profile. This is a constant delta B, delta H, which is the change in pressure, change in enthalpy. Okay, which means we are maintaining a constant delta B and delta H during our change in the profile. Okay, we also have different options, like we have a constant change in pressure, a change in UA. Also, we can have a constant change in pressure, change in area. This is an inlet pressure and outlet pressure, which means the inlet pressure, the pressure is constant and equal to the inlet pressure. So we are keeping our profile at constant pressure, which is the inlet pressure, or we are keeping our profile at constant pressure, which is equal to the outlet pressure. Okay, so now we have done enter all the information over here. We still, as I mentioned before, haven't solved our heat exchanger. So to solve our heat exchanger, we need to define the flow in the shell. So if we go up there, this is our shell, the LTS vapor and sales gas vapor, and the one in tube is moving inside this yellow tube. Okay, so after that we need to add the rest of information. Okay, so after adding our heat exchanger, we are going to add after that another spec. Okay, so this one we are going to add another specification. So it is not solved because the degree of freedom, we need to check the degree of freedom. So the degree of freedom must be equal to 0 to make sure that our heat exchanger will be solved. So beside the need to define the shell and the tube information, we need also to make sure that the degree of freedom is equal to 0. Here we are going to add another spec. The specification could be added from here, and this spec is the temperature approach. So this one we are going to name it the temperature approach, and the temperature approach type is the minimum approach temperature, and this one will be defined for the overall. So overall minimum approach temperature, we are having a specification equal to 5. Okay, so this information is really important to know in terms of design. So make sure you know all the definition, like what is Q equal UA delta T, what is logarithmic mean, what is the temperature approach, and so on. Okay, so the minimum approach temperature that we have defined above, this one, this is the minimum temperature difference between the hot and the cold stream, which means this heat exchanger will be functioning if the temperature difference is not less than 5 degrees Celsius. So if I am having the tube side with 100 degrees Celsius and the shell side with 95 degrees Celsius, my heat exchanger will be operating, because the temperature approach, or the difference between the temperature of the heat exchanger shell side and tube side, is equal to 5. If this temperature, the difference is 4 degrees Celsius, like the temperature in the shell is 100 degree and in the tube it's 96, the difference will be 4. So we haven't met this specification and it will be a problem. Okay, so again, the minimum approach temperature that we have defined to be 5 degrees Celsius is the minimum temperature difference between the hot and the cold stream, or the difference in temperature between the shell and the tube temperature. Okay, after that, in this case gas exchanger, we will find out that even if we have added another specification, the degree of freedom is lowered to 2, but my heat exchanger is still not solved. Okay, so in this case, after adding all the information, I have added all the information I have, and the degree of freedom is still equal to 2. So I'm going to make sure that I complete my solution or my case, and after that this one will be solved if this information like LTS vapor is defined. Okay, so now my gas is going to chiller. So in this case I am going to add a cooler to lower the temperature, and this cooler will be named chiller. Okay, so the inlet for this one will be the stream to chiller, and the outlet of this one gas to LTS. Okay, so if we check the outlet from here, okay, so gas to low temperature separator, which we are going to add later. Okay, so here we have added our material stream. We are required to add an energy stream, which will be our chiller Q or duty. Okay, so still we are asked about the delta B, and make sure always to add your delta B in the parameter section. So the delta B in this case will be 35 kilopascal. After adding this information, we are asked about the duty. Here, as I mentioned before, it is not recommended to add the information of duty if you are simulating a steady state of an actual plant. the chiller, it's always recommended to go to the worksheet. If you have an inlet temperature, you define the outlet temperature and the duty will be back calculated. Okay, so now I have added all the information I have. I don't know the exit temperature because I don't know the inlet temperature. Okay, so in this case I am going to add the low temperature separator. So here I'm going to add the low temperature separator, and next video we are going to define it.